In our last video, we talked about modeling in general, and now we're going to be looking a little bit closer at linear modeling. And a linear function shows a constant rate of change. The graph is a straight line. The rate of change is equal to the slope or the steepness of the line. The equation of a line in slope-intercept form is y equals mx plus b, where m is the slope, b is the initial value or the y-intercept, x is your independent variable, and y is your dependent variable. And here is an example in table form of a linear relationship. And you can see here that as my x values increase, their rate of change here is the same. And as the y values change, their change is the same. So this ratio of change of y to x, or y over x, is going to be the same throughout a linear relationship. And here is an example of a graph. Now this table that I have up here is the same as this graph down here. It shows the same relationship. On a graph, you can see that every time I go over 1 unit here, I go up 2 units. I go over 1 and then up 2. So this has a rate of change of 2. And I can see that from the equation right here. Remember that this is in the form y equals mx plus b. So 2 is my slope. That's where this triangle thing, or rise over run, comes from. This rise, how tall my triangle is 2. The run is 1. 2 over 1 is 2. That's where the slope comes from.
For these next few problems, we are going to follow these directions. We're going to describe the function in terms of the real-world meaning, determine the slope and express it as a rate of change, and then answer the question, is this a realistic model? Problem number 1. The title of this graph is The Distance an Airplane Travels. The horizontal axis, which represents the independent variable, is time in seconds. The vertical axis, which represents the dependent variable, is distance, which is measured in feet. So this graph is showing how the distance changes over time. Okay, to help us read this graph and understand what its meaning is, we are going to be choosing points on my graph that are right at the corner of one of these little boxes. And it doesn't really matter which of these points that you choose. We're going to start at the far left of the graph over here at 0, and then we are going to go over 2 seconds and up 1,000 feet. We go over another 2 seconds and we go up another 1,000 feet. And I can keep going over 2 seconds, up 1,000 feet. So the plane is traveling 1,000 feet every 2 seconds. Now, when we express this as a rate of change, we want to put our independent variable in the denominator, and we want to put our dependent variable in the numerator. So in this case, I'm going to have 1,000 feet over 2 seconds. And then I want to simplify this fraction. 1,000 divided by 2 is 500. So this is going to be 500 feet per second. That is my slope or rate of change. And the third question here is this a realistic model? Well, there's 2 things here that's going to make this a realistic model. First is my airplane needs to be traveling at a constant speed. We don't want to have this as like when the airplane's on the runway and taxiing down the runway and picking up speed, but it's a good model if the plane is in flight and at a constant speed. Okay? So that's the first thing. plane needs to be at a constant speed. And the second thing that's going to make this a realistic model is if this model is only good for a limited time. This plane cannot keep traveling forever. So it's only going to be for a certain amount of time. So in your homework, when you're asked about something being a realistic model, your answers are always going to go back to these 2 points. Do you have a constant rate of change, and is this good for a limited time?
Okay, the title of this graph is Draining a Swimming Pool. The independent variable is time in minutes, and my dependent variable is gallons. So you can see that over time, the gallons of water in the swimming pool is decreasing. I guess we're draining the swimming pool. Okay, we're going to look at the rate of change here with this problem in a slightly different way. And the rate of change is the change in the y values divided by the change in the x values. So as I go from this point to this point, any point along this line, I can find the change in the y values from point to point, divide that by the change in the x values, and that is my rate of change. Now in this problem, I think it's easiest just to use this point and this point, this whole graph here. The change in the y values. So to get from this point down to this point, I have this whole distance here of 2,000. But notice that to get from this point to this point, I'm going down. So the change in the y value is actually a negative 2,000. The change in the x value to get from here to here is 200. So these changes up here, negative 2,000 divided by 200. So that's a slope of negative 10. Okay, so the meaning of the rate of change here is that the pool drains at a rate of 10 gallons a minute. You may be wondering why I don't have a negative in this sentence, because I have a negative up here. And that's because I use the word drains in my sentence, so that indicates that the water level is decreasing.
In this problem, my independent variable is time, and my dependent variable is the snow depth in inches. And as we read this graph, I see that as I go over 4 hours, my snow depth goes up by 1 inch. Right? So go over another 4 hours and up another inch. So the depth of the snow increases 1 inch every 4 hours. Now remember, when we write this as a rate of change, we always want to put our dependent variable in the numerator and our independent variable in the denominator. So in this case, I'm going to have the dependent variable is the snow depth in inches. So I have 1 inch of snow every 4 hours. And when I simplify this, I can simplify this into 1/4 of an inch per hour. And is this a realistic model? Well, again, it's realistic if it's snowing at a constant rate. I mean, we don't want to have flurries for a few minutes and then a blizzard for the next few minutes. It needs to be constant snowfall. And this is only going to be good for a limited amount of time. It's not going to snow forever.
Okay, problem 3. The directions just say to answer each of the following and show your work. Water is leaking from a pipe at a rate of 2.3 liters per minute. How much water is leaked after 4 minutes? So 2.3 liters every minute, and we're doing that for 4 minutes. My answer is going to be 2.3 times 4, and that's going to be 9.2 liters. So then after 20 minutes, it's going to be 2.3 times 20, and that's 46 liters. Okay, and now we need to make a sentence for a relationship that goes on here. Something varies with respect to something else. This is always your dependent variable. And this blank over here is always going to be my independent variable. This varies with respect to this. That means that whatever's in this first blank is going to change depending on how much this thing over here changes. So liters leaked varies with respect to time. Problem number 4. Snow accumulates during a storm at a constant rate of 3.5 inches per hour. How much snow accumulates in the first 6.3 hours and in the first 9.8 hours? Let me give you a minute to pause the video and try to answer those questions. And there's your answer for problem number 4. Okay, now we're going to be looking at some different scenarios where we have a linear relationship going on, and we have to identify some things about these relationships. In this problem, we have Tom planted a 25-inch tree in his backyard, and each year the tree grows 4 inches. Okay, we're going to look at these first two questions together. What is the dependent variable and what is the independent variable? Now remember that a function shows the relationship between two sets of numbers. And one of my sets of numbers is fairly easy to recognize here. It's the height of the tree in inches. And my second set of numbers is actually the number of years. So which one is the dependent and which one is the independent? Well, how tall the tree is depends on how old it is. So the dependent variable is the height of the tree, and the independent variable is the number of years. Okay, the initial value or the y-intercept. So where does my dependent variable start at? Well, Tom planted the tree when it was 25 inches tall, so this is my starting value. And it represents the height of the tree when it was planted. Okay, now we're going to be looking at these next two questions. What is the slope and what does it represent? Remember, slope is the same thing as your rate of change. And what we want to do is look at the change of the height of the tree over time. Well, I know that this tree grows 4 inches every year, so that is my slope, and it represents how fast the tree is growing. And if we wanted to come back up here and put units with this 4 inches per year, we can do that. Okay, the next question, what is the equation of the line? Remember that the equation of a line is y equals mx plus b, where m is my slope and b is the y-intercept. And we've already determined that my slope is 4 and the y-intercept is 25. How tall will the tree be 5 years after it is planted? This 5 years is representing an x value. So I just need to put 5 into my equation and evaluate. So there's my equation, y equals 4x plus 25. So I'm going to have 4 times 5 plus 25. And that's going to be 45. So the tree is going to be 45 inches tall. And then the next question, how long will it take for the tree to be 65 inches tall? So this is my original equation, y equals 4x plus 25. And I want to know when will my y value be 65. So the height of the tree is 65, and I need to figure out what that x is. In order to solve this, I'm going to subtract 25 from both sides of my equation. So I have 40 equals 4x, and then I'm going to divide both sides of my equation by 4, and I get x to be 10. So it's going to take 10 years for that tree to be 45 inches tall. Okay, problem 6. The cost of car repairs is $200 for parts plus $50 per hour for labor. The dependent variable here is my cost, and the independent variable is the number of hours of labor. The initial value, or my y-intercept, is 200, and it represents the cost of the parts. Okay, now we need to identify the slope and what it represents. Slope is the rate of change, and we're looking at how the cost changes with respect to the number of hours. So the slope in this case is 50. And the slope is representing the cost per hour for labor. Okay, the equation of the line, remember, is y equals mx plus b. M is my slope, and we found the slope to be 50. And b is my y-intercept, or my initial value, and that is 200. And one thing I want to point out here is that if you wrote this equation as 200 plus 50x, then that's fine too for some of the problems in my math lab. Just be real careful on exactly how they want their answer written. Sometimes they want their x value first, and then sometimes it really doesn't matter to them. All right, the next question, what is the total cost if it takes 4 hours to fix the car? Okay, well, here's my equation, and I want to figure out the cost for 4 hours. Remember that this 4 represents an x value because it's representing the number of hours. So 4 is going to go in place of my x. So I'm going to have 50 times 4 plus 200, and that's going to be 400, so it's going to cost $400. The next question, if the total cost was 600, how long did it take to fix the car? Here's my original equation, and I'm going to put 600 in place of the y because the y is representing the cost. And then I solve, subtract 200 from both sides of the equation. So 400 equals 50x, and then divide both sides of the equation by 50. So x equals 8. So it took 8 hours to fix the car. Okay, next problem. A $1,200 washing machine and a laundromat is depreciated for tax purposes at a rate of $75 per year. Depreciated means that the value is going to be going down. The dependent variable is the value of the washing machine. The independent variable is the number of years. The initial value is $1,200, and it represents the initial value of the washing machine. Okay, the slope here is negative 75. Remember that the value is decreasing every year, so my slope is negative, and it's representing the value lost each year. Okay, and the next part is the equation of the line. Now, normally we write an equation in slope-intercept form of y equals mx plus b, but I'm going to sort of switch this around because I think that this problem makes a little bit more sense if we write this in a different order. The initial value of the washing machine is $1,200, and then it decreases $75 per year, so minus 75x. I think the answer written this way makes more sense. Now, if you wanted to write it as negative 75x plus 1,200, that's fine. So the value of the washing machine after 4 years, you're going to put 4 in place of the x, and you'll get $900. How long will it take until the value of the washing machine is 0? Here's my equation. I want to figure out the x value when my y value is 0. So this is my equation that I need to solve. Okay, we're solving for x. I'm going to add 75x to both sides of my equation. And then I'm going to divide both sides of the equation by 75. So x is 16 years. Okay, I'm adding in a couple of extra problems in this video. So my numbering is going to be off, so don't worry about that. You will have a problem like this in your homework. Problem number 9, it costs $500 to start a business selling t-shirts. Each t-shirt costs $4 to produce. What is the fixed cost in dollars? The fixed cost is the amount that doesn't change. That is going to be the $500. And what is the variable cost? The variable cost here is 4. Write an equation for the cost. I'm going to use x and y in my equation. Y is going to be my dependent variable. X is the independent variable. It's going to cost $500 to start up the business plus $4 for every t-shirt. And X is the number of t-shirts. Now, you may be asked to write this in slope-intercept form when you have the X first and then the 500. Just double check your directions in my math lab to see what they want. The next question is, how much will it cost to produce 40 t-shirts? Well, 40 is my value for X. So this is going to be 500
plus 4 times 40, and that's going to give me $660 for the cost. The next question is, how many t-shirts were produced if the cost was $820? Let me go back to my original equation. 500 plus 4x is equal to y, and y is the cost, and here I want the cost to be $820. So 820 equals 500 plus 4x. I'm going to subtract 500 from both sides of my equation. So I get 320 equals 4x, and then I'm going to divide both sides of my equation by 4, and I get x to be 80. So we've sold 80 t-shirts.
Okay, problem 8, the price of a certain model of boat is $6,000 and it rises at a constant rate of $200 per year. Write an equation to model the situation where x is the number of years and y is the cost of the boat, and determine the price of the boat after 3.5 years. We give you a minute to pause the video and try to do this problem on your own. And there are your answers. Now, if you had written this equation, as y equals 200x plus 6,000, that's okay as well. Okay, problem number 9. A tractor pulling a wagon on dry ground has a maximum speed of 10 miles per hour, and for each inch of mud, the speed decreases at 0.8 miles per hour. Write an equation to model the situation where x is the number of inches of mud and y is the speed of the tractor. Well, the maximum speed that we know is 10, so we can start off with the speed being 10, and then it's going to go down for every inch of mud. So the decrease is 0.8 times x. So there's the equation of the line, and I want to know at what depth of mud will the tractor be unable to move. So here's my equation that I'm looking at. And remember that this y value is representing the speed of the tractor. Well, if the tractor is unable to move, its speed is 0. So solving this equation, 0.8x equals 10, divide both sides by 0.8, and we get x to be 12.5 inches. Okay, these next few problems are just some more examples, just to give you some more practice. So if you have that handout that we have in class, then you can check your answers here for problems 10, 11, and 12. I'm actually not going to talk through these problems to show you the answers. The next problem I'm actually going to be talking about is problem 13, if you want to skip forward to that. Okay, problem 13. Anne made baby blankets to sell at the local craft fair. She spent $60 on the materials to make the blankets and $100 to rent the booth at the craft fair. If Anne sells the blankets for $40 each, how many must she sell in order to break even? Well, one thing that we have to remember here is the relationship between how much money she's bringing in and how much her expenses are. Okay, profit is income minus expenses. Okay, we're going to let P be profit. The income is how much money she has coming in, and she's bringing in $40 for every blanket that she sells, so 40 times X, where X is her number of blankets, minus the expenses. Now, she's spending $60 on material and $100 to rent the booth, so expenses are $160. I'll need to know how many blankets she must sell in order to break even. So in other words, when is my profit 0? So I have this equation that I need to solve. So she needs to sell 4 blankets.